Welcome back to Dave Does Math from Home. This is part 2 of our video on integration by parts. I usually write that somewhere. Section 5.5, part 2. There we go. Okay, this is part 2 of that video on integration by parts. Or integration by substitution. Sorry, I got confused by saying part 2 of the video. It's not integration by parts. That will come much later. Integration by substitution, 5.5. Here we go. In our first video, we sort of talked a lot about the theory of why this works and what's safe, what's not safe, and we went through with the chain rule. In this example, I just want to sort of go through the mechanics of integration by substitution, piece by piece, and hopefully it becomes clearer the more of these we do. The integration, or the mechanics of integration by substitution start with identifying pieces. We need the inside, we need the outside, and we need the other. These are the three pieces that we need to identify within this mess. The inside and the outside are the two pieces of the composite function. And this is the composite function. Square root of something else. Square root's on the outside, polynomial on the inside. This is the composite, so this bit's going to be the other. So the inside function is x to the 4th minus 7x. The outside bit is going to be the square root of something, which is also known as something to the 1/2. And the other function will be literally everything else, the entire other piece. So that's 4x cubed minus 7 dx. This is the identification step. The next step is we start to create things to substitute. So I'm going to set w equal to the inside, x to the 4th minus 7x. And then I'm going to find dw, which is always just the derivative of this. So if you take a derivative of this thing, you should get 4x cubed minus 7 dx. The next step is to see if these things match. If this matches this, then we're all set and we can proceed to the next step. If they don't match, there's a couple tricks we can do to try and make them match, and we'll cover those in another example in a second. But right now they match, so we're all set. So we can proceed to the substitution step. We're going to rewrite this. This equals the integral. I'm going to rewrite the integral without any x's. That's the goal. I need to completely extract all of the x's from this thing so that there's nothing left but w's. The inside-outside bit is always easy. Because you set w equal to the inside function, this whole composite bit should just become w to the 1/2. So it's just the outside function with a w in it. That's always going to be how the substitution goes when the substitution works. All of this here, 4x cubed minus 7 dx, since that matches dw, I'm just going to replace it with dw. Now, this weird, horrifying mess that involves composite functions and the products of other functions and a silly polynomial, all of this has been reduced to something extremely simple and straightforward. This is just w to the 1/2 dw. And we can integrate this very easily. Something to the 1/2 is going to turn into something to the 3/2. When you divide by 3/2, that's the same as multiplying by 2/3. And then we'll toss the c on the back end. This step honestly gets forgotten more than other steps. Lots of times students get so caught up in substituting and then unsubstituting that in between those two things they forget to actually integrate. Don't forget to integrate. The entire purpose of the substitution is to make this thing easy to integrate. You have to actually integrate before you can unsubstitute. So don't sleep on that. But then you do have to unsubstitute at the end. If the question is asked about x's, you can't give me an answer using w's. You got to give me an answer about x's. So, well, you get 2/3 of w was this business, x to the 4th minus 7x to the 3/2 plus c. And you're done. That's the whole thing. It goes pretty fast when you get used to it. Let's do another pretty straightforward example, and then we can start throwing wrenches in and see what happens. Let's look at the integral of (3x squared times e to the x cubed dx). First step is always identify. Inside, outside, other. The inside and the outside both come from the composite function. This is not a composite function. It doesn't have an inside or an outside. This is where the inside and the outside business happens. This is e to something, but that something is a function. So this is our composite bit. So the inside is going to be our x cubed. The outside will be e to the blob. And the other is going to be literally everything else. 3x squared and a dx. So we can set w equal to the inside. You can find dw. dw is always the derivative of this. That'll be 3x squared dx. And we check to make sure if it matches the other function. This is 3x squared dx, that's the derivative of this. This is 3x squared dx, it's the other pieces of this. Since they match, we can proceed to the substitution step. This thing equals e to the w. Again, this thing should always, once you substitute, this thing should always kind of just look like the outside function with a w in it times 3x squared dx is the same as dw. So we integrate e to the w, and we get e to the w plus c. And then we unsubstitute, and we get e to the x cubed plus c. And that's it, and we're done. So now it's time to do some weird stuff. Let's do one that looks pretty similar. Let's do the cosine. Let's do x cubed times the cosine of x to the 4th dx. Let me write this just a little bit better. The integral x cubed times cosine of x to the 4th dx. This is a lot like the one we just did with the e. We had a power function inside of an exponential. Now we have a power function inside of a trig. Let's see what's different. We need an inside, we need an outside, and we need another. I think the inside is pretty clearly x to the 4th, and the outside is pretty clearly the cosine of the blob, which means that the other is x cubed dx. Identification step finished. So far, so good. Now we're going to set w equal to x to the 4th. and then take the derivative of that. The derivative of x to the fourth is 4x cubed dx. And now we need to look at whether or not these things match. And they don't match. It's going to be a bit of a problem for us. Not a huge problem for us, but a little bit of a problem for us. Here's how we fix this problem. It's important to remember when doing these problems that coefficients are safe. These things don't match, but the only difference between them is a coefficient. Since coefficients are safe, that's a solvable problem. The only thing I need to make these things match is to put a 4 here. And I can do that. I can just put a 4 there if I put a 1/4 on the outside to balance it. 1/4, coefficients are safe, so 1/4 times 4 is 1. I haven't changed this problem in any way, I just changed the way it looks. But because I have a 4 in here now, these guys match. And since they match, I can do some substitutions. When you bring this down to substitute, the 1/4 that we created up here, that stays. That has to stay with us. The integral, cosine stays. X to the fourth, is it going to become a W? Nope. I started to write x to the fourth. Cosine W. The 4 and the x cubed and the dx. All three of these things, the 4 and the x cubed and the dx, all of those things are going to become GW. So we introduce the 4 to get these things to match. We introduce a 1/4 so that it's balanced, and we haven't changed it. The 4 gets sucked up into this piece and disappears. The 1/4 stays. And now we can integrate cosine. The integral of cosine, the 1/4 stays. The integral of cosine is sine. Toss the c on the back end there. And then we just have to unsubstitute. So this is going to be 1/4 sine of x to the fourth plus c. And we're finished. I'm going to do one more like this, and then we can start a third video where we talk about what to do with definite intervals. Okay, this time let's do the integral of x to the fifth over x to the sixth plus 7. 5, 6, and 7. Seems like a good one. We'll toss the dx in here for good measure. I mentioned earlier that when you have division problems, they get kind of horrifying, so it's best, generally speaking, it's best not to think of them as division problems at all, but to rearrange them as multiplication problems with some negative exponents involved. So that's what we're going to do here. First order of business, we're going to swap this out for the integral of x to the sixth plus 7 to the negative 1 times x to the fifth dx. So now there's no division involved, and at this point hopefully it's pretty easy to see why this is a composite function in the first place. So from here we can move forward with the identification plan. We need an inside, we need an outside, and we need an other. inside, according to these parentheses, should be x to the 6th plus 7. The outside should be something to the negative 1, and the other should be x to the 5th dx. So we set w equal to the inside, x to the 6th plus 7. We find dw. dw should be 6x to the 5th dx. That's the derivative of this thing. And then we check to see if they match. They don't match, but the only difference between them is a constant. Sorry, not a constant, a coefficient. The thing that is keeping them from matching is a coefficient, and that is a very fixable problem. I can just toss a 6 on here, no problem. Assuming my marker works, it won't be a problem. There's a nice big red 6. Let me see if my other red marker is a little better. 6. So I'm putting the 6 in there so that these guys match. To keep things balanced, I have to put a 1/6 outside. Now they match and everything's balanced, and I can move to the next step. I'm going to slide right down here. The 1/6 on the outside stays. This thing turns into a w to the negative 1. This whole piece turns into dw. And that's all that's left after this substitution. 1/6 w to the negative 1. It's nice and simple. The integral of w to the negative 1 is, it's natural log. It's always the natural log. Some of you were thinking, w to the 0, don't do that. This is that one weird exception to the power rule. It's the natural log of w. 1/6 stays. We have a natural log of w. I guess if we're being extremely pedantic, we should put absolute value signs here. Although I suppose we don't need them. X to the 6 plus 7 is always positive. So 1/6 natural log x to the 6th plus 7 plus c is our final answer. Stay tuned. There's a couple more things we got to talk about.